All right. Well, it is 3:30. I guess we can go ahead and get started. Hey, Isabella, Olivia, Rachel, and Yifan. How are you guys doing? Hopefully good. All right. Hey, I'm seeing some direct messages here. I think you guys should totally go for it. Yeah, like you guys can get the amount of engagement that you want in this class. So if I'm going too fast or too slow, yeah, definitely let me know. And yeah, definitely feel free to stop me and ask any questions that you might have. So we do have our homework assignment that is going to be due this Friday. As always, my office hours are now the regular resume time, Thursdays and Fridays. Sorry, my bad, just Fridays. So basically we've wrapped up with Unit 6, talking about how we might extend some of our clustering algorithms to purely categorical data sets, as well as mixed data type data sets. Now, I've posted Unit 7, which generally speaking is when I go ahead and dig into a few more clustering evaluation metrics that we didn't quite cover in our previous unit, Unit 3. Now, usually there's a lot of things that I like to cover in Unit 7, but what I've found is that, especially when I'm teaching online, things tend to go a little bit slower than when I'm teaching in person. So I think what I might do is actually just focus on this part here of Unit 7. I might skip over some of these other clustering evaluation metrics and introduce them at the end of class if we have time. But yeah, what I've found is that sometimes I run out of time and I don't get to really talk about some of the cooler clustering algorithms like spectral clustering in the end. So I think for now, I'll probably just focus on one more clustering evaluation metric that I'm going to introduce here. But if you are curious about any of this additional stuff, I can post some old videos from last semester if you're interested. But yeah, so one more clustering evaluation metric that might prove to be, useful, in contrast to some of the other clustering evaluation metrics that we've discussed in the past. So when we discuss, so this new clustering evaluation metric is going to be very similar to what the average silhouette score was telling us for a variety of different reasons. So number one, what we want to remember is that we actually used this average silhouette score to help us evaluate both the cohesion and the separation of single observations in a data set and in a clustering. It helped us evaluate the cohesion and separation of clusters within a clustering that we found. And finally, the average silhouette score, like we saw, helped us evaluate the overall cohesion and separation of the entire clustering of the given data set. So what we're going to introduce in Unit 7 is what we call a cluster sorted similarity matrix, which is also going to help us evaluate the separation and cohesion of a single observation, each cluster in a clustering, and the entire clustering of a given data set. So let's talk about some of the drawbacks that we have seen with using the average silhouette score or the silhouette score of a given observation. So for instance, below is the silhouette plot for a given clustering of a given data set. So just as a recap, the first question is, I'm going to post a poll. Based on what we see here, are there any objects in this data set that are closer to another cluster than the one that they're actually assigned to? Okay, so try submit in the next few seconds. Oh, okay, cool. Yeah, so most of us say yes, and that is, in fact, something that we can see here. So for instance, we see a few observations in these silhouette plots that have negative silhouette scores. So for instance, this observation here. So what that tells us is that there is an observation For instance, in cluster 3, that is closer on average to the observations in some other cluster. Yes. For instance, there is at least one observation in cluster 3 that is on average closer to the observations in some other cluster. Okay. But the next question is, based on what we can see here in the silhouette plot, can we tell which cluster this observation is closer to? Try to submit soon. Okay, yeah, so that's right. So unfortunately, one of the downsides of using the silhouette scores or a silhouette plot, which shows us all of the silhouette scores, is that this is not something that this clustering evaluation metric can explicitly tell us. And then on top of that, simply just by looking at this silhouette plot, the final question here is, can we determine how close each of these clusters are to each other based on this plot? Oh, excuse me. Okay, so try submit in the next few seconds. Right. So yeah, so unfortunately, another downside of this silhouette plot is it doesn't actually tell us how close a given observation is, or for instance, another cluster is to any other cluster in the data set. All it really tells us is the ratio of a given observation to the average distance of observations in the cluster that it's assigned to, and the average distance it is to basically observations in its closest cluster. But it doesn't actually tell us the distance between two clusters, for instance. So this is going to be one benefit of using the cluster sorted similarity matrix. So it can basically help us answer those two questions. So the way that we create this matrix is relatively straightforward. So basically we have our data set here. So let's just say we're looking at our shill bidding data set, and we had, let's just say, clustered just the numerical variables. So let's just say maybe we used k-means to cluster these numerical variables. So we came up with this set of k-means cluster labels here. So to create your cluster sorted similarity matrix, you add the cluster labels as one of the columns in your data set. All right. And then you simply just sort that matrix, excuse me, that data frame, by the corresponding cluster label. So therefore, all of your observations belonging to cluster 0 are all put together first. All of your observations belonging to cluster 1 are sorted and put together second, so on and so forth. And then the final step is to create a, basically keeping that order using just the numerical variables or just the variables that you ended up clustering. Take that data frame in the corresponding sorted order and create a distance matrix with that data set here. And you can put it into a heat map to basically visualize each of those pairwise distances between each observation in that sorted data set. And usually what we end up doing is we create a resorted order, if you will. So this would be, for instance, the resorted index 0, 1, 2, 3, so on and so forth. Okay, so by interpreting this cluster sorted similarity matrix, we can basically examine the cohesion and the separation of our clustering within the given data set and learn more about, a little bit more about each of those clusters, as well as observations within each cluster. So, for instance, what I could have figured out based on, like, let's just say my clustering here, I could have figured out, for instance, that there were 500 observations that corresponded to cluster 0. So what that tells me, actually, so this is a slightly different data set. So for instance, when I had clustered my data set, a different data set, what I might have seen is that there were about 500 observations assigned to cluster 0, about 500 observations assigned to cluster 1, 500 to cluster 2, and 500 to cluster 3. So that gives me an indication in the cluster sorted similarity matrix as to which observations are corresponding to which of the following 4 clusters here. So this is actually our data set that we have clustered, and these are the 4 clusters that we've created. And this is the corresponding cluster sorted similarity matrix. And you want to keep in mind that we were using the Euclidean distance, measure the distance between each pairs of observations. Okay. And so let's try to interpret what this cluster sorted similarity matrix is telling us. Let's see here. Hopefully you should be able to see all of what I've written here. So the first question is, based on what we can interpret in this cluster sorted similarity matrix here, hold on one second. Is this going to work? All right, let me slightly rearrange this here. Let's just say this is 1, this is 2, this is 3, this is 4. So basically what I'm going to ask you here in just a second in a Zoom poll is, based on these 4 clusters, which I have identified on the x-axis here in the similarity matrix, which of these 4 clusters corresponds to this green cluster here that I see in the scatter plot? So let me open up a poll. Okay, so cluster 1, 2, 3, or 4. Which one is the green cluster? So think about it. Try to submit in the next 15 seconds. Okay, and just make sure that you're using this labeling that I've created here. So I just want to just emphasize that I slightly changed up the labeling here just so I could ask a better Zoom poll, basically. So this is cluster 1, 2, 3, 4. Okay. All right. So hopefully the changing up of the labeling didn't make this too confusing here. But yeah, so we can see that this green cluster here, based on what we can see in the scatter plot, is going to correspond to this cluster 2 here. The green cluster corresponds to cluster 2. So we can see, for instance, that the observations in cluster 2, basically cluster 2, is about equidistant between this cluster, this red cluster here, as well as this blue and orange cluster here. So we can see that reflected in cluster 2 here in the distance matrix, where, for instance, we can see that the average distance the observations in this cluster are from, these other 3 clusters here, on average are a lot lower in comparison to whatever this cluster is here. So we can see that, for instance, this cluster does in fact have another cluster in which it's comparatively much further away from, with much larger distances like these here. So that gets to my next question. So I'll relaunch another Zoom poll. So which of the clusters displayed below is going to correspond to the red cluster visualized here? Okay, so try to submit in the next 5 seconds. Okay. All right. Yeah, so majority of us say that this red cluster corresponds to cluster 1. And so that is the correct answer. So for instance, we can see that cluster 1 is somewhat close to cluster 2. And so we can see that reflected here, that basically this cluster 1 is somewhat close to cluster 2, but it is comparatively a lot further away from clusters 3 and 4. So we can see that reflected here with the larger distances as well. So the question is now, though, does the blue cluster or the orange cluster correspond to cluster 3, for instance? And I'll actually tell you, it's, based on what we can see here in the similarity matrix, we can't really actually distinguish the blue cluster from the orange cluster, because basically in this block here, this is where we're going to see all of the intra-cluster distances for the observations assigned to either the blue or the orange cluster, we're not sure. And this block here represents all of the intra-cluster distances between the observations in either the blue or the orange cluster. So we're not sure. And what this block here represents is all of the distances that exist between cluster 3 and 4. So in other words, all of the distances between the blue and the orange clusters. So we can see that, because we're dealing with this similar set of clusters that we've seen before, where they're non-convex, they're nested within each other, by using simply just the Euclidean distance metric to measure separation between the clusters, we see that, we weren't actually able to really identify that these 2 clusters, the blue and the orange, were in fact actual meaningfully separated clusters. And so we can see with our eyes, right, that there is in fact actually this meaningful separation between the blue and the orange. But because these 2 clusters are non-convex and they're not well separated, what we can see here is that our cluster sorted similarity matrix was not actually able to detect a meaningful separation that exists between them, at the very least if we're using the Euclidean distance. However, we are actually able to, extract useful insights here. We are actually able to say, for instance, that, cluster one is in fact much further away from some other clusters. We are in fact able to, get this meaningful insight that, cluster two, well, it's very cohesive, right? Because we see this strong intra-cluster distances for the observations within, cluster two. And it is relatively well separated from the other clusters, but it's not as well separated as, for instance, cluster one is from some of the other clusters here. So the nice thing about this cluster sorted similarity matrix is it allows for us to measure cohesion. So for instance, how small are the intra-cluster distances? It allows us to compare that cohesion to the overall separation. So by looking at the inter-cluster distances, between sets of observations in each cluster. And then also further tells us, for instance, how far apart on average are the clusters from each other. And then on top of that, it also gives us an indication not just to evaluate the cohesion and separation of clusters within a given clustering, but it also allows for us to examine even just individual observations as well. So for instance, we can see here, let's focus on maybe like this particular bar here, so something like that. So what that is indicating to us, actually, let's focus on, so this one right here. So this tells us that, let's just say this is, let's just say that this cluster 3 is the blue cluster. So what that indicates to us is that there's some observations which are comparatively a little bit closer to cluster 1 than, for instance, some observations also in cluster 3. So something more like this, which are more yellow, which are comparatively a lot farther away on average to cluster 1. So by looking at the individual bars, this can give you an indication as to, on average, how far away that observation is from all observations in the data set in each of the clusters. So this can be another way for you to, for instance, identify, the existence of outliers and, for instance, how close is that given observation, to other clusters individually speaking. Okay. So this basically just gives us more of a nuanced way of exploring the clusters that we found with a given data set. And basically, this can be a really useful tool because, again, as we've been seeing, not all of our clustering algorithms and not all of our clustering evaluation metrics are going to agree with each other. So for instance, if you find that, two of your clustering algorithms disagree with each other, this similarity matrix might be a useful tool or a useful diagnostic tool to use to perhaps explore, well, why did we get different results? So basically any evaluation metric that gives you more insights into the nature of your high dimensional clusters can be useful to essentially help you determine, what's going on behind the scenes, essentially. So to basically just kind of, answer some of these additional questions here, what we might say is that all of the clusters are, we can say cluster 1 and cluster 2 are very cohesive and well separated from other clusters. We can specifically say that cluster 1 is further away from clusters 3 and 4 than cluster 2 is. Okay. And furthermore, we might say, at the very least, if we are using Euclidean distance to measure distance or to measure cohesion and separation, then clusters 3 and 4 are not suggested to be cohesive and well separated. And this is because the average intra-cluster distance of cluster distances of clusters 3 and 4 is comparable to the average inter-cluster distances between cluster 3 and 4. Okay. All right. So any questions on that? Okay. So if we want to implement this in Python, it's not all that difficult to do. So basically just using some basic pandas manipulation functions. So we'll use our shell bidding data set again. Okay. And let's just say, for instance, we wanted to cluster this data set using k-means. And so we clustered it with 4 clusters. Okay, and again, this is just our numerical variables here. Okay, and so let's just say, for instance, we wanted to explore a little bit more about our clustering that we just found. So we can basically take our k-means cluster labels and add them as a new column in my DF data frame. Okay, I've done all this before, so I'm not gonna do this again. Okay, and so if I want to create my cluster sorted similarity matrix, I can take my data frame and sort the rows by that k-means cluster label column that I just created. This creates my sorted data frame. Okay, and then before I actually make my similarity matrix, I do want to make sure that I'm only putting the numerical variables, or only the variables that I had clustered in this resulting data frame. So using that same sorted order that I just created, I'm going to drop all of the variables that I don't want to put in the simulated matrix. So I'm going to drop the pre-assigned class labels as well as the k-means cluster labels. And so I'll overwrite my sorted data frame to be just this. Okay. And then I'm going to use that pdist function that I've used in previous units. Okay. What you want to remember is pdist, it'll create this, this distance matrix for you, but it'll be a flattened distance matrix. So you want to basically unflatten it and put your similarity or distance matrix into a square form. Okay. And then if you simply just want to put a similarity matrix into a heat map, you can use this color mesh function. And you also want to use this color bar, so we can basically interpret what each of those colors mean. Okay. And so we get our cluster sorted similarity matrix here. And so for instance, we want to actually interpret that. Here's how we might go about doing that. So for instance, one of the key things when it comes to interpreting these matrices is you want to make sure you know what set of reordered index values correspond to which cluster, if you will. So if your clustering is relatively cohesive and well separated, what you would ideally hope to see is basically a block of dark blues on each of, where each of those clusters show up on the diagonal, and blocks of, relatively yellow values on the off diagonal. But if it's ever unclear, you can actually use, for instance, the value counts function on your predicted cluster labels column. And so basically what this does by itself, this simply just counts up how many observations correspond to cluster 0, how many observations correspond to cluster 1, so on and so forth. And then we can sort by the index just to make sure that, these values are, or these cluster labels are in ascending order. And then we can use the cum sum function to basically, take the number of observations in cluster 0 and then add that to the number of observations in cluster 1. So basically, the total number of observations in cluster 0 and 1 is this value here. The total number of observations in clusters 0, 1, and 2 is this number here. So this basically gives you an indication as to where the cluster 0 and cluster 1 basically the demarcation point, if you will, between cluster 0 and cluster 1. This gives you an indication as to the demarcation between cluster 1 and cluster 2, so on and so forth. Okay. So, for instance, what this can tell us is that, our clustering that we found here is, relatively cohesive and well separated. So we do see, on average, very smaller intra-cluster distances for each of the 4 clusters here, in comparison to each of the, average inter-cluster distances between pairs of clusters. And then on top of that, for instance, we can see that clusters 0 and 1 are comparatively, much further away from each other than, let's just say, clusters 0 and 2, right? And we see the same thing here. So clusters 2 and 3 are relatively, further away from each other. But for instance, cluster 2 and cluster 1 are comparatively a little bit closer to each other. Okay. So just more insights that you can extract about your clustering, which can be useful when you're trying to actually, so the whole point here is, there's many different results that each of your clustering algorithms might be able to return to you. And you want to make sure that the results that you're returning to like your boss or your client are in fact actually meaningful, right? Because nobody's going to reach out their hand from their computer and slap your hand and say, no, you shouldn't be using k-means in this particular case. You can always use k-means. Whether or not your k-means clustering result is going to be meaningful, that's a different story. So using clustering evaluation techniques like this can help build further corroborating evidence, for instance, that the clustering result that you're actually returning is in fact meaningful. So for instance, I do see that there is this relatively decent separation that exists between the 4 clusters here. So that builds one layer that I am in fact, returning, meaningfully separated points as opposed to just cutting up a blob. And then on top of that, for instance, I do see, when I plot those k-means cluster labels in my TS&E plot, I do also see this further indication that there is this separation that exists between my 4 k-means cluster labels. So that builds this additional layer of corroboration. But now the downside of the TS&E plot is, like we said, we don't actually know how far apart each of those clusters are from each other. So by using the cluster sorted similarity matrix, we can actually get more of a sense as to how separated they are. So actual numbers, if you will. Okay. All right. Any questions on that? Okay. All right, cool. So, so hopefully we'll have time to come back to some of these other clustering evaluation metrics, but in the interest of, hopefully getting, being able to cover the more interesting clustering algorithms in the end, I think we'll just kind of move right along to Unit 8, which is not going to be an evaluation metric, but it is going to be another clustering algorithm itself. Okay, so in Unit 6, we talked about basically how we can take all of our numerical clustering algorithms and extend it to categorical data sets. So now we're going to switch gears again, and we're going to introduce another clustering algorithm that, again, is only intended to be used for purely numerical data sets. However, though, as with, as like what we saw with k-means and the TS&E algorithm and our hierarchical agglomerative clustering algorithms, if you wanted to extend the techniques that we're learning here with this version of DBScan, to work with categorical data sets, there are some, basic changes that you could make to the algorithm to get it to work in a very similar way. So generally speaking, the main change that you end up making for a lot of these clustering algorithms is to change the distance metric. So change the distance metric such that it's more useful for measuring the distance between different types of data sets that you're looking at here. But the bullet point is the dbScan algorithm that we're going to introduce here is going to be designed for numerical data sets. So let's focus on why we might want to introduce another type of clustering algorithm. So I've seen this data set before, right? So back in Unit 2, we've described a variety of different ways in which we might define a cluster. And what we saw is basically the way that we can, define a cluster is actually going to dictate the most appropriate type of algorithm for identifying this cluster here. So I'll actually say now, so this type of data set here, we have yet to actually introduce a clustering algorithm that will effectively be able to identify the clusters that we can see here with our eyes. So just as a recap, what, based on the clusters that we can see here with our eyes, what cluster definition best describes what we're seeing here? So is it like a prototype-based cluster? Something else? So one of our homework assignments was talking about this data set, I think. Does everybody have any good, fun weekend plans? Yeah, so we're describing, so what we're seeing here is dense clusters surrounded by sparser sets of observations. So what we just described here is the density-based cluster definition. Okay, and again, what this is, or what a density-based cluster is a set of observations in a more dense cloud, or a more dense cloud of observations. That exists in a field of less dense points, which oftentimes we consider to be noise. Okay. So what we discussed is that many of the clustering algorithms that we've talked about so far tend to not work as well in the presence of noise. So k-means tends to not work as well with noise. The TSNE algorithm tends to perhaps sometimes, display misleading clusters that might exist when it's actually simply just noise. Now, sometimes even if we run the k-means clustering algorithm, even if we run a hierarchical agglomerative clustering algorithm on a given data set with noise, it is possible that the algorithm still, might be able to identify, the actual clusters that you're looking for. So for instance, it might actually be effective at splitting up your data set like this, or like this is a cluster, this is a cluster, so on and so forth. But the fact of the matter is, for each of the clustering algorithms that we've discussed so far, every observation that gets put into a clustering algorithm will, in fact, be placed in at least one cluster. And so what we can see with our eyes is that, we don't actually really even necessarily want these noise points to end up in a cluster. It'd be great if we could use a clustering algorithm that puts our density-based observations in a cluster and then is able to weed out any of the noise points that we see, or any of these less dense noise points that we can see here, and simply just label it as noise. So as of right now, none of our clustering algorithms is designed to do that. They're not designed to identify clusters and weed out the noise. So that's one of the benefits that the dbScan clustering algorithm that we're about to introduce can in fact bring us. So dbScan stands for density-based spatial clustering of application with noise. And it's actually going to be very different from all of the prototype-based clustering algorithms that we've seen so far, because we're now actually not, we don't actually need to specify the number of clusters that we'd like to see. So what that means is that it's actually possible that, you'll run your dbScan algorithm not knowing how many clusters it's actually going to return. The number of clusters it returns is simply the number of clusters that it returns. However, we are going to specify two sets of parameters that we do need to think carefully about when running the dbScan algorithm. So the first parameter that we specify is this epsilon radius that we're going to draw around each point in the data set. Okay. And then the second parameter that we need to specify is this min points number. And so basically this min points is going to be the number of points that we are going to be looking for that exist within a given epsilon radius around each point that we're considering. So for instance, what I'm going to do in this example below is I'm going to specify that my min points is going to be 3. So what that means is that I'm going to be looking to see, does a given point have at least 3 points within its epsilon radius, including the point itself. So that's a key thing here. Okay, so for instance, this observation would in fact have 3 observations, or the around within its epsilon radius, if you will. That includes the point itself. So once you've specified your parameters, what you're going to do is scan through each of your observations in the data set and either label it as one of the following. So you're either going to label it as a core point, a border point, or a noise point. So the first scan of your data set, you're going to look to see if a given observation is what we call a core point. So an observation is a core point if it has at least the number, or at least the min points number of observations within its epsilon radius. So for instance, we would inspect this point here. And so if our min points is 3, we can see that this is not a core point because there are not at least 3 points within its radius. And we can see this point is not a core point because there are not 3 observations within its epsilon radius. However, this point here is in fact a core point because it does have 3 points within its epsilon radius. So this point here in the center would be a core point. Okay, so this is a core point. This is a core point. This is not a core point. This is not a core point. This is a core point, and this is not a core point. So we would label each of our core points that we've identified first. Okay. All right, so once we've identified all of our core points, we're going to go through another pass of the remaining observations. And we're going to determine if each of these remaining observations are what we call a border point. So an observation is considered to be a border point if it is not a core point, but it is within an epsilon radius of a core point. So this is not a core point, and it is not within an epsilon radius of a core point. So this is not a border point. However, this is a border point. So is this. So is this. And so is this. So we label each of our border points as such. Okay. And so we go through a final pass of the observations in the data set. And we simply just say any point that has not been identified to be a core point or a border point is simply just called a noise point. We would label this as a noise point. Okay. All right. Questions on that? All right. So once we have labeled every single one of our points in the data set, the final step is to actually cluster the observations. So what we do is we first look at our core points. And so what we say is, if two core points are within an epsilon radius of each other, they are going to connect in what we call a bubble path, and they will in fact be in the same cluster as each other. Okay, so basically these two core points are within an epsilon radius of each other, so they'll connect. And these 2 points are within an epsilon radius of each other, so they will connect as well. Okay, but this core point is not within an epsilon radius of any other core points, so it will not connect with any core points. So we said that these 2 core points will connect. These 2 core points will connect. So they will be in the same cluster. So what that tells me is that all 3 of these points will be in the same cluster. And this point will not be in the same cluster. Okay. And then the final step is, once I have clustered my core points, I also cluster my border points as well. So I assign each of my border points to their closest core point. I would assign these border points to these core points. Okay. And so I have created 2 clusters here. So all of these points connect in one cluster, and all of these points connect in one cluster. We've got cluster 1 and cluster 2. Okay. And so the nice thing, like we mentioned about the dbScan algorithm, is that any point that is considered to be a noise point will be left out of the given cluster. So it's simply just labeled as noise. We don't want to cluster it, and we call it a day. Okay. So this is how the dbScan clustering algorithm works. All right, I'm about to put you guys in Zoom rooms where we're going to go through a couple more exercises going through the dbScan clustering algorithm. So any questions on how this works? Okay. All right, so that's what I'm going to do next. So what you'll see here is we have the same data set. And what we'd like to do is cluster this data set 4 times using each of the following sets of epsilon and min points parameters. So we're going to cluster the data set using this set of parameters, this set of parameters, this set of parameters, and this set of parameters. Okay, so I'm going to open up the breakout rooms. I'll let you guys choose your rooms. Let's see here. 1 second. All right. Okay, so I just opened up the rooms. You can choose your own room. In the interest of time, I'm just going to start randomly assigning people, so you can always change it if you like. And then we'll meet back and discuss in about like 5 or 6 minutes. Okay. All right, so welcome back. Give people a few more seconds to come back. So I'm curious to hear what you guys came up with. So for the first question, in which we're using a epsilon radius of square root of 2, so basically that's this distance here, and a min points value of 5, how many clusters did we find and how many noise points did we find? Yeah, so we have 2 clusters, and then yeah, so the rest of the stuff that doesn't end up in the clusters are noise points, and so there's actually going to be 3 noise points. So let's go through this here. So basically, I've set this epsilon ball to basically have a radius of square root of 2. So first, let's look for core points in our data set. So this is, this point does not have, or this epsilon radius does not have 5 points within it. Neither does this. Neither does this. Now this point does have 5 points within its epsilon radius. So this is a core point. This is not a core point. Neither is this. Neither is this. But this one is. So we identified 2 core points in this data set. Meet our specifications. So this is a core point. And this is a core point. Okay. So next we look for the border points. So this is not a border point because it is not within an epsilon radius of a core point. Neither is this. However, this point is a core point because it does have, this point is a border point because it does have a core point within its epsilon radius. So this is a border point. So is this. So is this. So is this. Now this is not a border point because it is not within a epsilon radius of a core point. But this one is, so is this, and so is this. So we label each of our border points. I'll just do B. Okay. And so the remaining observations are simply just going to be labeled as noise. So this is a noise point, this is noise, and this is noise. Okay, so the final step is to create the clustering. However, we can see that actually none of our 2 core points are going to connect in the same cluster because they are not within an epsilon radius of each other. So no core points are going to connect. So all that we have left to do is assign each border point to its closest core point. Okay, so all of these points are together in a cluster. And all of these points are together in a cluster. All right. Any questions on that? Okay, cool. So what about question B? So with this set of parameters, how many clusters did we get and how many noise points did we get? Yeah, exactly. So we have 1 cluster and 2 noise points. Okay. So we have weakened the parameters or weakened the requirements for a point to be considered to be a core point. So now we only need to have 3 points within the epsilon radius for a point to be labeled as a core point. So still, this is not a core point. Neither is this. Neither is this. This point still is, in fact, a core point. This one is not. Now this one, so this point here is, in fact, going to be a core point. So is this. So is this. This. Yeah, but not this one. Okay, so we would label our core points as such. Okay, so this is a core point. So is this, this. Okay, and let's see here. This one, is this a core point? No, so this is not a core point here. Okay, so now we look for the border points. So this is not an epsilon. This point is not within an epsilon radius of a core point. Neither is this. However, this point is within the epsilon radius of a core point, so it's a border point. Same thing with this. This is a border point. So is this, and this. Okay. So we label our border points. Okay. And so the next step is to cluster the observations. So these two core points here are within the same radius or epsilon radius of each other, so they're going to connect. These points are going to connect. These 2 points are going to connect, and so are these. So all of these core points will now connect and be a part of the same cluster. Okay, and the final step is to assign each border point to its closest core point, like that. Okay, so this all becomes one cluster. And the remaining points, i.e. those that were not labeled as core points or border points, those are our noise points and they are left out. They are not clustered. All right. Any questions on that? Okay, cool. All right, so part C, we've actually made our specifications for being a border point, a core point extremely loose. So when we have a epsilon radius of 1 and a min points value of 1 as well, how many clusters do we get and how many noise points do we get?
We figured out that there would be all of the points would be core points and there would be no border points or noise points.
Mm-hmm. And so how many clusters does that turn into then?
The number of points that are on the plot, which I did not count.
Okay, but yeah, you got it. So yeah, so we end up having 13 singleton clusters, return of the singleton again, and we have 0 noise points, right? So we've kind of, created this very contrived set of parameters that actually are not going to give us the most informative clustering, but it's useful to know to give us a sense as to what kind of clustering results we get as we tweak these parameters. So we just encountered a situation in which we've set our min points to be just 1. So it's exactly what Justin just said. So if we set our min points to be equal to 1, then basically what that means is that every point gets to be its own core point. So basically we only need 1 point within our epsilon radius. So this is a core point, this is a core point, so on and so forth. So we would first label all of those core points. Okay. What that tells us is that every observation is going to be assigned to a cluster. However, we've basically set the stage for us to get all singleton clusters in this data set because we've set our epsilon value to be smaller than the distance of the 2 closest observations in this data set, right? So basically there's going to be no observation. So basically no 2 core points are actually going to connect to each other in a bubble path. So in other words, no two observations are going to be within the same cluster. So this is a cluster, this is a cluster, so on and so forth. Okay. So that's a property of the dbScan parameters that we just identified here. So let's actually skip ahead and actually define that. So specifically, when the min points is set to be 1, then what we just observed, and which is actually going to, hold for all scenarios, is every point will be a core point. Okay. And so based on how you set that epsilon value, what that means is, you may get like these singleton clusters, or it is possible if you had set that epsilon value larger, you could have had some observations that connect. But bullet point, if you set min points to be equal to 1, you're not going to get any noise. Okay. All right, so let's move on to the final scenario. So we have set our parameters again to be not the most useful when it comes to clustering this data set. So now we set our epsilon value to be 1 and our min points value to be 3. So how many clusters did we get and how many noise points did we get? Yeah, all noise, no clusters, exactly. So 0 clusters and 13 noise points. Right. So again, we've set that epsilon value to be too low, such that basically no point will actually have any other observation within its epsilon radius. And then furthermore, we've made it more challenging, actually impossible in this case, for any point to actually be considered a core point. So basically we're saying every point needs to have at least 3 points within its epsilon radius, including itself, but we've set that epsilon radius to be too small. So therefore, none of these observations are core points. And because there's no core points, there can't be any border points as well. So therefore, every point is just considered noise. Okay, so in all likelihood, this is not going to be the most useful result of your algorithm. So you want to be careful about setting your parameters in which basically your epsilon radius is smaller than the 2 closest points, and then your min points is set to be greater than 1. So what we just described here is this scenario here. So with that set of parameters that you want to watch out for, it'll be the case that every point is considered to be noise. There are no clusters. Not the most useful. Try to avoid that. Okay. All right. Any questions on that? All right. Good job, y'all. Okay, so we want to think a little bit more carefully about what kind of an impact these parameters have. So let's just say, for instance, we have plugged our data set into a TSC plot, and we have somewhat of a sense as to how many clusters exist in our data set. Now, without thinking carefully about how we set our min points or our epsilon values, we can get all sorts of results that don't necessarily correspond to the rough number of clusters that we think that we might be looking for. So we want to think about what kind of an impact changing our min points and our epsilon values are going to bring about to the overall clustering. So let's first think about what might happen if we either decrease our min points parameter or increase our epsilon value. So when it comes to what's going to happen to our old core points, border points, and noise points, these changes are going to have very similar effects. So let's think about what happens if we were to, let's just say, increase our epsilon value. So we have an existing clustering with a existing epsilon value here. So this was a core point, this was a core point, these were all border points, and this is a noise point. So the question is, if we were to increase that epsilon value, what do we think is going to happen to our old core points? Is it possible for them to revert to border points or perhaps noise points? Or is it always going to be the case that if you were originally a core point and we increase the radius, will you remain a core point? That's the question. Yeah, exactly. So if we increase that radius, we've basically made it easier, not harder, for a observation to be considered a core point. So the old core points, if you increase the radius, will remain core points. Okay. Now let's think about what happens to our old border points. So this used to be a border point because it didn't have enough observations within its epsilon radius. So if we increase the epsilon radius, then it's possible for our border points to become core points. Okay. However, for instance, we don't increase that epsilon radius enough, then it's still possible that that border point would still remain as a border point. But the question is, if we increase our epsilon radius, is it possible that that border point could suddenly become a noise point? That's the question. Yeah, no. Yeah, exactly. So basically, we're making it easier for a border point to either fall within the range of a core point or become a core point itself. So basically, it's not gonna, it doesn't have the opportunity to become a noise point where we're broadening its scope, not restricting it. Okay. And so then we want to think about what's going to happen to our old noise points. So we have an old noise point and we increase the epsilon radius, then it's entirely possible that that old noise point could remain a noise point. However, if we, let's just say we're talking about this one here, if we increase the epsilon radius a little bit more, then it's possible, for instance, like this point right here used to be a border point, but perhaps now it's become a core point. So therefore, this noise point could have become a border point. Also, it's possible if we keep increasing that epsilon radius, then that noise point could, in fact, have the required number of points within its radius to also be considered a core point as well. Okay, so the old noise point could also become a core point. Okay, and so, if we decrease the min points requirement, then it also is going to have a similar effect as well. So we're basically making it easier for an observation to be considered a core point. So therefore, we're making it easier for noise points and border points to basically jump up the queue, if you will. Okay. Now, the real question is, well, if we decrease the min points or increase the epsilon, what kind of an impact is this going to have on the number of clusters that we're actually looking for? Well, so depending on the nature of your data, increasing the epsilon value could actually lead to two competing effects, if you will. So it's possible that if you increase your epsilon value, let's just say, then your core points, which were previously disconnected, could actually now become connected to each other. So this would lead to fewer clusters in the data set. On the other hand, though, it's possible that, for instance, for instance, if you were to decrease so for instance, if the number of core points had increased, so let's just say, for instance, this, this became a core point and this became a core point, but they were core points that were not within the epsilon radius of any of the other core points, then sometimes what you can end up seeing is that like a whole bunch of previous noise points turn into these singleton core points that don't connect with any larger clusters. And therefore, this could lead to an increase in the number of clusters. So basically, if the number of core points increases, or your epsilon increases, then this could actually lead to two competing effects. So therefore, it's useful to consult multiple other evaluation metrics to give you a sense as to what the right parameter values are to help you extract the most amount of meaningful insights from your DBSCAN cluster analysis. So on Tuesday, we're going to talk about some of these techniques that might help us, tune these parameters. But these are some things that, you want to be thinking about. So unfortunately, there's not this direct relationship between changing the min points and the epsilon values to, the number of clusters that you might end up getting. Okay. All right. Questions on that? All right. So just a little bit more and then we'll call it a day. So here's one such technique that can be used to first even just determine if DBSCAN is an appropriate algorithm to use. But number one, we can also use these techniques to give us a sense as to what an ideal set of parameters might be. Okay, so let's just say we have this data set here. And so what we can create, or what we end up creating to give us more insights about DBSCAN, is what we call a k nearest neighbors distance plot. So what we would do, so for instance, if we wanted to create a k equals 2 nearest neighbors distance plot, is we would find the distance of a given point to its actual closest neighbor. So generally speaking, and just like we saw when talking about DBSCAN and counting the point itself, in these k nearest neighbors plots, we actually are also considering the point itself. So for instance, if we created a k equals 1 nearest neighbors distance plot, we would actually be finding the distance of a given point to itself, or its closest neighbor is in fact considered to be itself. So when we talk about the k equals 2 nearest neighbors plot, we're actually saying what is the distance a point is from its actual closest neighbor. That's like a distinct point. So we can find each of these nearest neighbor distances for each points in our data set, and we can sort them in ascending order and then plot each of those distances. So this is square root of 2, this is 4, this is 5. Okay? And so basically, this k nearest neighbors plot, specifically this k equals 2 nearest neighbors plot, can give us an indication as to how many noise points might actually exist in the data set, if there's any noise points at all, right? So we can see here that the majority of our points, their nearest neighbor is relatively close. So it's within a square root of 2 distance from each other. And then we see this large jump in the nearest neighbor distance values. So this might be an indication to us that our data set has 2 noise points, and that using DBSCAN is going to be a useful algorithm to help us identify those 2 noise points, essentially. And then in addition, what we're going to talk about on Tuesday is it's going to give us a sense as to what kind of DB scan results we're going to end up seeing with a certain epsilon value. So what we're going to do is we're going to draw a horizontal line at this epsilon value. And basically based on whether a given point falls below or above this line, this is going to give us an indication as to what kind of point it will be labeled as. And it'll give us more indication as to what we might expect in our algorithm. Okay, but we'll talk about that on Tuesday. Okay, all right, so we are out of time. So I will stop recording.